Okay, the mirror equation. So this is our mirror equation where we have 1 over the focal length. So this applies to both convex and concave mirrors. This is the distance to the image, and this is distance to object. So, because these are all in the denominators, we definitely get to practice with our fractions. Oh goody. And as far as that relates to this situation over here, so let's say, alright, so here is our mirror, alright, and that's a concave mirror, and we have a focal length, and we have some object, and we'd say one ray goes in parallel and out through the focal point, and then we'd say one ray goes in through the focal point and out parallel. And let me redraw that. And out parallel. Aha! See how they cross right there? Alright, so there's our image. So when we talk about focal distance of the focal point, etc., it means this, just so you have this in your notes, this right here is distance to focal point, and this right here would be distance to the object, and then I'll use a different color. This right here would be distance to the image. Okay, so that's what we're talking about. So now instead of just drawing the ray diagrams, we're going to be able to calculate it as well as draw a ray diagram to verify. So here's our situation. Before we even get into, let me bring it back here. Before we even get into the ray diagram, let's look at the information we have. Do you see how the focal length is 3? And this could be centimeters or meters or whatever. We will be dealing with centimeters in class. The 1, 2, 3, 4, 5 distance to the object is 5, and from that we can calculate everything else. So it goes like this: 1 over the focal length equals 1 over the distance to the object plus 1 over distance to the image. Alright, we're going to subtract 1/5 from both sides, and let's zoom in. Alright, we're going to subtract 1/5 from both sides. So we have 1/3 minus 1/5, which equals, common denominator is 15, so we have 5 minus 3 over 15. 2 over 15 equals 1 over distance to the image. Alright, so what this tells us, if we were to cross multiply, is that distance of the image is 7.5 whatevers. So let's fill that information in. So we got 7.5. Let's draw a ray diagram. So one ray goes in parallel out through the focal point, in through the focal point, and out parallel. Alright, so let's see, where did I got that at about 7. And out parallel. Aha, look. So, perfect, Torville. Right there at 7.5. So we got 5, 6, 7, and 7.5-ish. Okay. From here we'll probably calculate the magnification. Okay, so magnification is, we have negative distance of the image over distance of the object. So this is negative 7.5 over 5, which is negative 1.5. So we'll write that in. So notice two things. One, magnification is negative, so the image is upside down, right? The object is right side up, or upright, and the image is upside down, so it's negative, and the image is 1.5 times as tall as the object. Okay, from this we can calculate the image, height of the image and height of the object. We don't really know those, so I'm just going to leave those blank for now. Okay, that was cool. So you might want to, if you're an adventurous physics student, put this on pause. That's your pause button right there, and go ahead and try to solve this. If not, I will. So Distance to the object is 1. Distance to the focal point, or the focal length of the lens, is 3. And from this we can calculate. So we're going to say 1 over 3 equals 1 over 1 plus 1 over d sub I. Subtract 1 from both sides, so we have 1/3 minus 1, which is a negative 2/3, equals 1 over d sub I. Cross multiplying tells us that distance to the image will be negative 3/2. Negative 3/2. Okay, so if we have a negative distance to the image, everything over here is a positive distance. A negative is going to be behind the mirror. So in the previous notes, we didn't do a concave lens where the image is in really close, where it's closer than the focal length. What happens is you're going to get a larger image, and it's going to be a virtual image. So here's how the ray diagram goes. We go light as if it had come from the focal point, hits the lens and goes out parallel, and then light that hits the lens parallel goes out through the focal point. So what the eye would perceive is this, where those two cross, we have the image. So this is a virtual, because it takes place behind the mirror. The light doesn't actually cross, but that's what you would see. It would look like it's behind and larger. So what did we get? We got that the distance to the image is negative 3/2, so this is negative 1, negative 2, negative 1.5 right there. And our magnification would be negative of negative 3/2 over 1, which is 3/2. So notice that the magnification is positive. This thing is upright. It is 3/2, so it's 1.5 times as tall as that. So we could, and we could calculate these if we need them. Cool. So now we have two examples, convex. Let's see what we know. We know that the focal, for convex, the focal length or point is always negative. So write that in there. And I think we talked about that, but I'm just being super specific. What we did is we were drawing ray diagrams, and we always use the focal point on the other side. Well, we take that into account mathematically as well. So we're going to say that the focal length is negative 2. Distance to the object, 1, 2, 3, 4. And distance to the image, well, we don't know. So let's do a little calculating. 1 over the focal length equals 1 over the distance to the object plus 1 over distance to the image. So I'm going to subtract 1/4 from both sides, and we have negative 1/2 minus 1/4, which is, you guessed it, negative 3/4 equals 1 over d sub I. We could cross multiply or just flip the fractions, and we're going to get that the distance to the image is a negative 4/3. Okay, so let's write that in and see what happens when we draw our ray diagram. Oh, ouch, just my elbow. I kind of like this green color, so let's see, it goes in like this, and then as if it had come from the focal point on the other side, it will do that. And then this is where I was drawing this cheater line. Yeah, I'm going to go for it. Let's see. So that's pretty good. Alright, so there's my little cheater line, meaning light that comes in like this is going to go out like that. And where do we get? Let's see, this goes, and we zoom in, and they cross. So this was not the best approximation. Alright, we were looking for negative 4/3, so this would be negative 1, and then that was more like a negative 5/3. Torville. Oh well. So But the bottom line is that you're going to have graph paper and a ruler, and you're going to be getting answers that are really, really similar to what you calculated from the mirror equation. So, again, this would be a virtual image, and the magnification, so I'm just going to write that word so that the students do. That's you. It's a virtual image. Magnification is going to be negative of the distance to the image over the distance to the object. You have that formula. And if we divide and stuff, this is going to tell us that the magnification is 1/3. Notice how it is a positive number, so the image is upright, and notice that the little arrow here is about 1/3 the height of that. Makes sense. Okay, last up. Another convex, so again we know the focal point is negative. We're using this one. Here's our object, so we can say that the focal length is -3. Distance to the object is 1. Looks a little weird. Well, let's see what happens. Okay, so 1 over -3, this is 1 over f, equals 1 over d sub o plus 1 over d sub I. We're plugging into the mirror equation. We're going to subtract 1 from both sides. So, -1/3 minus 1 equals 1 over d sub I, and -1/3 minus 1 is -4/3. Right. So, if we cross multiply, we're going to end up with d sub I equals -3/4. Let's try it. Okay, so how does this ray diagram thing go? In parallel, out as if it had come from the focal point. So again, remember this is for a convex lens. And then this guy goes in like this as if it were going to the focal point and then out. And then this goes. Okay, this is not as easy as it looks. Maybe it doesn't look easy. That would help. Alright, and let's see. So I'm supposed to get -3/4, but it's not looking so hot. So let's just say, oh, and look, they intersect right here. Ha ha ha. Okay, you try it on the iPad with the stylus thing. Alright, so does this work? Oh yeah, look, our image is just where we anticipated it would be, and the magnification is, let's see, negative of the distance to the image, so negative of -3/4 over 1, so 3/4. Magnification is 3/4, and it's positive, so this is definitely upright, and yeah, sure, it looks like, after I faked it, like about 3/4 the height of the object. Okay, so those are more examples of ray diagrams and using the mirror equation to actually calculate where these things should be. Should be being key there. Ha ha ha.